Imagine, for a moment, the absolute silence of the Martian night. It is a stillness so profound that it feels heavy, pressing against the rusted rocks and the fine crimson dust that has settled over the landscape for millions of years. Today, Mars is a world of ghosts, a quiet, frozen desert where the only movement is the occasional ghost of a dust devil dancing across a dry crater floor. But was it always this way? Has this planet always been a graveyard of ancient rivers and vanished seas? To find the answer, we have to look beyond the silence. We have to peel back the layers of red dust and look into the cooling heart of a planet that once beat with the heat of creation. Our journey doesn't begin on the surface we see today. To truly understand Mars, we must travel back in time, not by centuries, but by billions of years, to the very dawn of our solar system. If these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. 4.5 billion years ago, there was no red planet. There was only chaos. Our young sun was a tempestuous newborn, surrounded by a violent, swirling vortex of gas and debris known as the protoplanetary disk. Picture a massive, glowing whirlpool stretching across the void, filled with microscopic grains of ice, silicon, heavy metals, and elementary gases. This was the cosmic nursery, a place of extreme heat and unimaginable kinetic energy. In this disk, gravity began to play its long, patient game. Tiny specks of dust collided and stuck together, driven by electrostatic forces. These tiny clumps grew into pebbles, then boulders, and eventually into objects kilometers wide, the planetesimals. In the region where Mars would eventually reside, the environment was a frantic demolition derby. These planetesimals, half-formed worlds, slammed into one another at thousands of miles per hour. Some were shattered into dust, while others, the victors of these collisions, grew larger and hungrier, pulling in everything around them. This was the process of accretion, the violent birth of a world. But Mars was born in a peculiar neighborhood. It occupied a zone where the building materials of the cosmos were both abundant and strangely limited. Have you ever wondered why Mars is so much smaller than Earth or Venus? It's one of the great lingering questions of planetary science. Mars grew large enough to become a distinct, independent world, but it never reached the true heavyweight status of its neighbors. It formed as a borderline planet. It was massive enough to generate its own heat and hold on to an atmosphere for a time, but it lacked the sheer bulk needed to maintain that internal fire for billions of years. It was as if the cosmic construction crew ran out of bricks just as the foundation of Mars was being finished. Because it was smaller, its fate was sealed from the very beginning. It was destined to live fast and cool down early. But in those first few 100 million years, Mars was anything but cold. Imagine a world not of red dust, but of glowing orange fire. During its infancy, the entire surface of Mars was a vast, roiling ocean of magma. This wasn't just a few volcanoes. It was a global sea of liquid rock, thousands of miles deep. The heat was generated by the constant, relentless bombardment from space and the decay of radioactive elements trapped deep within its belly. Everything that fell from the heavens, massive asteroids, icy comets, stray chunks of metal, melted instantly upon impact, adding its mass to the glowing cauldron. This magma ocean was a crucial stage in the planet's biography. As the liquid rock swirled, a process called differentiation began. Gravity pulled the heaviest elements, mostly iron, nickel, and sulfur, down toward the center. This sinking metal formed the Martian core, a massive, dense heart that would one day determine the planet's survival. Meanwhile, the lighter silicates floated to the top, eventually cooling to form the first, fragile crust. It was a world of extremes, a thin, hardening shell of stone floating over a restless, fiery interior. And then came the era of the Great Bombardment. The early solar system was still cluttered with the leftovers of creation, gigantic fragments of rock and ice that hadn't yet been cleared away. For hundreds of millions of years, Mars was used as target practice for these cosmic projectiles. One of these impacts was so colossal that it changed the face of the planet forever. An asteroid the size of a small island, perhaps hundreds of miles across, slammed into the southern hemisphere. The energy released was equivalent to billions of nuclear bombs. The result of this cataclysmic event is still visible today: Hellas Planitia. It is one of the largest impact basins in the solar system, a crater so deep and so wide that you could fit half of Europe inside its rim. But these impacts did more than just leave scars. They churned the Martian crust, bringing hot rocks to the surface and releasing trapped gases. They accelerated the cooling of the interior while providing the energy needed for the first great era of volcanism. They were violent, yes, but they were also transformative, creating the mineral diversity and the structural foundations that would later allow for the presence of water. As the magma ocean finally began to solidify, Mars started to resemble a true planet. Beneath the hardening crust, the mantle was a place of immense pressure and heat, where plumes of molten rock rose and fell in a slow tectonic dance. And at the very center, the core was doing something extraordinary. Because it was still liquid and spinning rapidly, it acted like a giant dynamo. This movement generated a powerful magnetic field, an invisible shield of energy that wrapped around the young planet. This magnetic shield was the most important asset Mars ever had. It was a barrier that stood against the solar wind, the constant stream of high-energy particles flowing from the sun. As long as this shield was strong, Mars was protected. It could accumulate an atmosphere. It could hold on to the water vapor being belched out by its thousands of erupting volcanoes. This was the golden age of Mars, a time when the planet had everything it needed to support life. If you could stand on the surface of Mars 4 billion years ago, you wouldn't recognize it. The sky wouldn't be the hazy pink or butterscotch color we see today. It might have been a deep, bruised blue, or even a thick, misty grey. The air would have been dense and heavy, filled with carbon dioxide and steam. And then the rains began. As the planet cooled, the water vapor in the atmosphere condensed. For thousands, perhaps even millions of years, it rained on Mars. The water didn't just sit on the surface, it moved. It carved paths through the volcanic plains. Small trickles became streams, and streams grew into roaring rivers. These were not the gentle brooks we think of today. These were massive, deep torrents that cut through the Martian crust with the power of 1,000 floods. They formed channels that we can still see from orbit billions of years later, silent, dry riverbeds that serve as a testament to a world that was once vibrant and fluid. At this point in history, Mars was a world of blue and grey. In the northern hemisphere, where the land sits much lower than in the south, the water began to gather. It filled the vast impact basins and low-lying plains, forming the first Martian seas. There is strong evidence to suggest that a great northern ocean once existed, covering nearly a third of the planet's surface. Imagine the sound of waves crashing against volcanic cliffs under a thick, cloudy sky. Imagine the smell of sulfur and rain. This was a world with a pulse, a world with a future. But the tragedy of Mars was already written into its size. Because it was smaller than Earth, it couldn't hold onto its heat. A smaller planet has more surface area relative to its volume, meaning it radiates its internal energy away into the cold vacuum of space much faster than a giant world like Earth or Venus. Slowly, the Martian interior began to settle. The convection in the mantle slowed down. The bubbles of molten rock grew smaller and less frequent. And most importantly, the core began to change. The liquid iron and nickel that had been spinning so energetically started to thicken and solidify. The dynamo, the engine that created the magnetic shield, began to sputter. It was a slow, agonizing process that took hundreds of millions of years, but the outcome was inevitable. The magnetic field began to flicker, growing weaker and more unstable. Without its shield, Mars was naked. The solar wind, which had been deflected for eons, now began to strike the upper atmosphere with full force. It was like a sandblaster stripping paint off a wall. Molecule by molecule, the Martian atmosphere was being carried away into deep space. The protection was vanishing, and with it, the planet's ability to stay warm and wet. But before the final freeze, Mars lived through one more incredible epoch. The crust had fully hardened, and the atmosphere was at its thickest. This was the moment when the Martian engine was at its peak. Volcanoes rose to heights that would make Mount Everest look like a foothill. The rivers were wider than the Amazon, and the lakes were as deep as any on Earth. Even as the core was cooling, the surface was a masterpiece of geological activity. Today, we look at the Martian landscape and see a wasteland. We see the dust, the rocks, and the silence. But every one of those rocks has a story to tell. They remember the heat of the magma ocean. They remember the shock of the great impacts. They remember the weight of the water that once flowed over them. Mars was not born as a desert. It was forged as a world of fire and water, a world that had every intention of becoming a home for something more than just dust. As we move forward in our journey, we will explore how that water shaped the land and how the disappearance of the magnetic field turned a blue world into the red desert we know today. But for now, just remember that under the cold, silent surface of the modern Mars lies the memory of a planet that was once alive with the roar of volcanoes and the rhythm of falling rain. It was a world that, for a brief cosmic moment, stood on the threshold of life. This was the birth of Mars. This was the beginning of the end. And in the next chapter, we will look at the era of the great waters, the time when the red planet was, for a while, a blue planet. Close your eyes and try to imagine a sound that hasn't been heard on Mars for 3.5 billion years. It isn't the whistle of a thin, freezing wind or the crunch of a robotic wheel on dry sand. It is the sound of a heavy, rhythmic roar, the sound of a massive waterfall plunging into a deep, rocky basin. Imagine the misty spray catching the light of a distant, pale sun. Imagine the scent of wet stone and the sight of clouds heavy with rain scudding across a thick, grey-blue sky. This was not a dream. This was the reality of the young Mars, a world that we are only now beginning to truly see for what it once was, a planet of water. When we look at Mars through the lenses of our modern telescopes and orbiters, we see a global cemetery. We see thousands of miles of dry, winding valleys that look exactly like the riverbeds of Earth. We see massive deltas where silt and mud once settled at the mouths of ancient lakes. We see minerals that can only form in the presence of liquid water, clays, sulfates, and carbonates. The evidence is overwhelming. Mars was once a blue planet, or at least a world where blue was a dominant feature of its geography. But how did a planet so far from the Sun, in a solar system where the young Sun was actually 30% fainter than it is today, manage to stay warm enough for water to flow? This is the great mystery of the Noachian epoch, the first billion years of Martian history. To understand it, we have to look at the atmosphere. In its youth, Mars wasn't the thin-aired ghost we know today. Its atmosphere was a thick, protective blanket, likely dozens of times denser than its current state. Volcanoes across the Tharsis Plateau and the Elysium region were constantly erupting, belching out massive quantities of carbon dioxide, water vapor, and sulfur dioxide. This created a powerful natural greenhouse effect. This blanket of gas trapped the sun's warmth, preventing it from escaping back into the cold void of space. Even though the young sun was weaker, this atmospheric insulation was enough to keep temperatures above the freezing point, at least in the lowlands and the deep craters. Imagine the weather on this ancient Mars. It wouldn't have been the static, frozen calm of the modern era. It would have been a world of cycles. Water evaporated from the seas, formed thick clouds, and fell back to the surface as rain or snow. For millions of years, this cycle carved the face of the planet. Scientists call these valley networks. When you look at images of regions like Margaritifera Terra or Oxia Palus, you see dendritic patterns, branching networks of small streams feeding into larger rivers, just like the veins of a leaf or the tributaries of the Mississippi. These weren't just temporary trickles caused by melting ice. These were stable, long-lived river systems that flowed for thousands of years. They tell us that the Martian climate was once stable enough to support a global hydrological cycle. There were rainy seasons. There were floods. There were periods where the sound of running water was the heartbeat of the planet. But Mars didn't just have gentle rivers. It was also a world of absolute, terrifying catastrophe. Scattered across the Martian surface are features known as outflow channels, and they are unlike anything found on Earth. Imagine a river channel not a mile wide, but 50 miles wide. Imagine a flood so powerful that it moved boulders the size of houses and stripped the bedrock bare in a matter of days. These were the mega floods of Mars. Channels like Casset Valles and Ares Valles serve as the scars of these events. How does a planet create a flood that dwarfs the Amazon? The answer lies beneath the surface. As the Martian climate began to fluctuate, large amounts of water were trapped underground as permafrost. In some areas, vast reservoirs of liquid water were held back by thick dams of ice. But when a nearby volcano erupted or an asteroid struck the surface, the heat would suddenly melt that ice. The pressure would become unbearable, and the ground would literally burst open. Millions of tons of water would explode onto the surface in a single moment, carving massive canyons and carrying enough sediment to bury entire continents. If you were standing in the path of such a flood, the wall of water would have been hundreds of feet high, moving with the speed of a jet engine. Yet, between these violent outbursts, there were places of profound peace, the lakes. For the last 2 decades, our robotic emissaries, the rovers Spirit, Opportunity, Curiosity, and Perseverance, have been our eyes on the ground, searching for the memory of these ancient waters. They have found it in the craters. Consider Gale Crater, the home of the Curiosity rover. Gale is a massive impact basin with a mountain, Mount Sharp, rising from its center. As Curiosity climbed the foothills of this mountain, it didn't find just volcanic rock. It found layer upon layer of lakebed deposits. Billions of years ago, Gale Crater was a vast, deep lake. For tens of thousands of years at a time, the water was still and calm. Fine silt and clay settled to the bottom, trapping minerals and perhaps even the organic building blocks of life. Curiosity found rounded pebbles, stones that had been tumbled and smoothed by a flowing stream before being deposited into the lake. It found mudstones that cracked as they dried out billions of years ago. The lake in Gale Crater wasn't a fluke. It was a persistent environment that could have supported microbial life for millions of years. And then there is Jezero Crater, where the Perseverance rover is currently working. Jezero is a masterpiece of ancient geography. From orbit, you can see a perfect river channel cutting through the crater rim and spilling out into a massive fan-shaped delta. On Earth, we see these deltas at the mouths of the Nile or the Mississippi. They only form when a river flows into a stable body of standing water for a long, long time. Jezero wasn't just a lake, it was a sanctuary. The delta acted as a natural filter, trapping the most interesting minerals and organic matter in its layers of sand and clay. As Perseverance drills into these rocks, it is essentially reading a history book written in mud. Each layer represents a different season, a different century of Martian history. It tells us of a time when the water was neutral, not too acidic, not too salty. Exactly the kind of water you would want to find if you were looking for a place where life could begin. But the most ambitious theory of all concerns, the Oceanus Borealis, the Great Northern Ocean. If you look at a topographic map of Mars, you'll notice something striking. The northern hemisphere is significantly lower than the southern hemisphere. It is a vast, smooth lowland that covers nearly a third of the planet. For decades, geologists have pointed to features that look like ancient shorelines tracing the edge of this basin. If these theories are correct, the northern plains of Mars were once filled with a sea that contained more water than the Arctic Ocean on Earth. Imagine standing on the edge of the Arabian Plain, looking north. Instead of a red, dusty horizon, you would see a vast expanse of dark, cold water. There would be waves, driven by the winds of a thick atmosphere. There would be icebergs breaking off from the southern highlands and drifting into the deep northern basins. This ocean would have been the engine of the Martian climate, regulating the temperature and providing the moisture for the rains that fed the river networks in the south. It was a complete, working world. So, what happened? Why did the blue fade to red? The tragedy of Mars's water is inextricably linked to the death of its magnetic field, which we discussed in the first chapter. As the planet's internal dynamo slowed down, its protective shield vanished. The solar wind began to strip away the atmosphere, layer by layer. As the air grew thinner, the pressure cooker effect of the atmosphere began to fail. Have you ever tried to boil water at the top of a high mountain? It boils at a lower temperature because there is less air pressure holding the molecules down. On Mars, the pressure dropped so low that liquid water became unstable. If you were to place a cup of water on the Martian surface today, it would either freeze solid instantly or boil away into vapor. There is no middle ground. As the atmosphere thinned, the greenhouse effect collapsed. The planet began to freeze. The Great Northern Ocean didn't just disappear. Much of it likely sank into the ground and froze, becoming a massive global layer of permafrost hidden beneath the dust. The rivers slowed to a crawl, then turned to ice, and finally evaporated into the thinning sky. The rains stopped. The clouds vanished. The roar of the waterfalls was replaced by the absolute crushing silence of a desert. But the water didn't leave without leaving a legacy. It changed the very chemistry of the planet. When the water reacted with the iron-rich volcanic rocks, it created iron oxides. Essentially, the planet started to rust. This rusting of the Martian surface is what gave the planet its iconic red color. The red planet is, in a very literal sense, a rusted world, a monument to a time when it was drenched in water. Today, we find the remnants of this era everywhere. We find it in the blueberries, tiny spheres of hematite found by the Opportunity rover, which form only in groundwater. We find it in the massive glaciers of water ice hidden under the dust of the mid-latitudes, enough ice to cover the entire planet in an ocean dozens of feet deep if it were all melted. We find it in the recurrent slope lineae, dark streaks on crater walls that some scientists believe might be caused by modern briny water seeping out of the ground during the Martian summer. Mars is still a world of water, but that water is now a prisoner. It is locked in the polar caps, buried in the soil, and hidden in the crystalline structure of the rocks themselves. As we look at the dry deltas of Jezero and the silent canyons of Valles Marineris, we are looking at a world that almost made it. We are looking at a twin of Earth that took a different path. The era of water on Mars was a window of opportunity, a billion-year stretch where the conditions for life were present. Whether life actually took hold in those ancient lakes and seas is the question that drives every mission we send to the Red Planet today. In the next chapter, we will explore the monumental architecture that this water and the planet's internal fire left behind. We will climb the highest mountains in the solar system and descend into the deepest canyons ever discovered. We will explore the geography of the giants. For now, remember the sound of the rain on the ancient Martian rocks. It is the sound of a past that refuses to be forgotten, a blue memory buried under a sea of red dust. If you were to hover high above the Martian atmosphere, far enough to see the planet as a single, rotating marble, you would notice something that defies the logic of almost every other world in our solar system. Mars is a planet of two faces. It is as if two different worlds were stitched together along a jagged, uneven seam. This is the great Martian dichotomy, a geographic asymmetry so profound that it has puzzled scientists for centuries. The southern hemisphere is a rugged, ancient land, scarred by billions of years of asteroid impacts and rising high into the thin air. The north, by contrast, is a vast, smooth lowland, sitting miles below the southern peaks, appearing almost like a drained ocean bed. But this is only the beginning of the story. As you descend closer to the surface, the true scale of Martian architecture begins to reveal itself. This is not a world of subtle hills or modest valleys. This is a world where geography has been pushed to the absolute limits of physics. Here, mountains don't just peak, they pierce the very edge of space. Canyons don't just divide the land, they rip across the face of the planet like a global wound. Today, we explore the geography of the giants. The Great Divide, a tale of two hemispheres. To understand the surface of Mars, we must first address the split personality of its crust. Imagine a line drawn roughly along the equator. To the south, you have the highlands, a chaotic, cratered landscape that looks very much like the surface of the moon. This is the old Mars, a record of the violent early days of the solar system, where every impact remained frozen in stone. Some of these regions sit nearly 3 miles higher than the northern plains. But when you cross over to the north, the world changes instantly. The craters vanish, replaced by thousands of miles of flat basaltic plains. This is the Vastitas Borealis. Why is the planet so lopsided? This is one of the most debated questions in planetary science. One theory suggests a catastrophic origin, that a colossal object, perhaps the size of a small continent, slammed into the northern pole billions of years ago, literally stripping away the upper crust and leaving a massive, depressed basin. Another theory points to the interior, suggesting that massive plumes of heat rising from the mantle pushed the southern crust upward while allowing the north to settle and sink. Whatever the cause, this asymmetry dictated the entire history of the planet. When Mars was wet, the north was the basin for its oceans. When the winds blow today, they accelerate across these smooth northern plains, creating the global dust storms that define the modern Martian climate. The dichotomy is the foundation upon which all other Martian giants were built. Valles Marineris, the scar of a world. As we move toward the equator, we encounter a feature so massive that it can be seen from the other side of the solar system. This is Valles Marineris, the Mariner Valleys. If you were to place this canyon system on Earth, it would stretch from New York City all the way to Los Angeles. It is over 2,500 miles long, 120 miles wide in places, and drops to a staggering depth of 7 miles. To put that in perspective, the Grand Canyon in Arizona would be nothing more than a tiny, insignificant crack in the floor of Valles Marineris. Standing on the rim of this canyon would be a terrifying experience. The opposite wall would be so far away that it would likely be lost in the atmospheric haze. The drop beneath your feet would be so deep that you could stack 7 Mount Everests on top of each other and still not reach the top. But how did such a monster form? Unlike the Grand Canyon, which was carved over millions of years by the persistent flow of the Colorado River, Valles Marineris was born from the inside out. As the nearby Tharsis Plateau, which we will visit shortly, began to swell with volcanic magma, it put an impossible amount of stress on the Martian crust. The planet quite literally began to crack. Imagine a giant balloon that has been overinflated until the surface begins to tear. These tears became the foundations of the valleys. Later, as we discussed in the previous chapter, water played its part. Massive floods surged through these tectonic cracks, widening them, smoothing the floors, and carving secondary channels. Landslides, triggered by Martian Marsquakes, sent billions of tons of rock tumbling into the abyss, creating the jagged, tiered walls we see today. In the depths of these canyons, we find layers of sedimentary rock, mineral records of ancient lakes that once sat in the darkness of the gorge, protected from the winds above. At the western end of this system lies the Noctis Labyrinthus, the labyrinth of night. It is a dizzying maze of intersecting valleys and fractured plateaus. From above, it looks like a shattered pane of glass. It is a place of profound geological confusion, where the crust has collapsed into a series of deep, angular pits. It is here that the interplay between volcanic swelling and tectonic fracturing is most evident, a geometric graveyard of stone. The Tharsis Bulge, the planetary tumor, just to the west of Valles Marineris, sits a region that defies imagination. This is the Tharsis Bulge, a massive volcanic plateau that rises 5 to 7 miles above the surrounding plains and stretches for thousands of miles. It is so heavy that scientists believe its very presence may have caused the entire planet of Mars to tilt or roll in space billions of years ago, shifting the location of the poles. The Tharsis region is home to the most impressive collection of volcanoes in the solar system. 3 of them, Arsia Mons, Pavonis Mons, and Ascraeus Mons, sit in a nearly perfect diagonal line. Each one of these is a giant, rising over 10 miles high, but they are all dwarfed by the king of all mountains. Olympus Mons, the peak of the gods. Standing alone on the edge of the Tharsis Bulge is Olympus Mons. It is, quite simply, the largest volcano in the solar system. It is a shield volcano, much like the ones found in Hawaii, but on a scale that is almost impossible to grasp. Olympus Mons stands 13.6 miles high, nearly 3 times the height of Mount Everest. Its base is so wide, about 370 miles, that if you stood at the foot of the mountain, you wouldn't even be able to see the peak, because it would be hidden behind the curvature of the planet. If you placed the base of Olympus Mons over the country of France, it would cover almost the entire nation. Why did a planet smaller than Earth produce a mountain so much larger? The answer lies in the fundamental difference between Earth and Mars, plate tectonics. On Earth, the crust is divided into moving plates. As a volcanic hotspot erupts, the plate above it moves, creating a chain of smaller volcanoes, like the Hawaiian Islands. But on Mars, the crust is a single, static block. It doesn't move. This meant that for hundreds of millions of years, the magma plume beneath Olympus Mons stayed in exactly the same spot. Layer after layer of lava piled up in the same place. building a mountain that grew higher and wider than anything Earth's moving crust could ever allow. The gravity on Mars, which is only 38% of Earth's, also helped. It allowed the mountain to grow taller before its own weight would cause it to collapse or sink into the mantle. Climbing Olympus Mons would not be a steep trek. Because it is a shield volcano, its slope is very gentle, only a few degrees. In fact, if you were walking up it, you might not even realize you were climbing a mountain until you looked back and saw the horizon falling away. But as you reached the summit, you would enter a world where the sky turns black. The peak is so high that it sits above the majority of the Martian atmosphere. You would be standing on the threshold of space, looking down at the red dust of the planet as if from a satellite. The plains of silence and the sea of dust. Beyond the mountains and canyons lie the vast plains. These are the basaltic seas of Mars, massive fields of ancient lava that have been smoothed over eons by the wind. In the north, these plains are covered by a fine, powdery dust that is rich in iron oxides. This is the Red Sea of Mars. The dust is not just a coating, it is a dynamic force of nature. Because the Martian atmosphere is so thin, it takes very little energy for the wind to pick up these microscopic particles. Occasionally, a storm begins in a single crater. But because there are no oceans or mountain ranges to break the wind, the storm can grow until it envelops the entire planet. For months at a time, the giants we have discussed, Olympus Mons and Valles Marineris, can be completely hidden under a global shroud of crimson dust. In some regions, the wind carves this dust into spectacular dune fields. In places like the Proctor Crater or the North Polar Erg, we see dunes that look remarkably like the ones in the Sahara or the Namib Desert. But on Mars, they move with a glacial slowness, shifting only a few feet over decades. They are the fingerprints of an atmosphere that is dying, but still has enough strength to leave its mark on the land. Hellas Basin, the deepest wound. Finally, we must mention the Hellas Basin in the southern hemisphere. If Olympus Mons is the highest point, Hellas is the lowest. It is a massive impact crater over 1,400 miles wide and 4.3 miles deep. It was created by a collision so violent that it likely shook the entire planet to its core. The floor of the Hellas Basin is a strange, alien place. Because it is so deep, the atmospheric pressure at the bottom is significantly higher than on the rest of the planet. It is one of the few places where, if the temperature were right, liquid water could theoretically exist for a short time without boiling away. It is often filled with a thick white fog of carbon dioxide ice or dust, making it look like a pale, ghostly eye on the surface of the planet. The sleeping giants. When we look at the geography of Mars today, we are looking at a world that is geologically asleep. The volcanoes are silent. The canyons are no longer stretching. The floods have long since vanished. But the scale of these features tells us of a time when Mars was a world of incredible internal energy, a world that burned with a fire that dwarfed anything on Earth. Mars is a world of superlatives. It is a place where nature took the basic building blocks of a planet, rock, heat, and gravity, and used them to create monuments on a scale that we are only beginning to understand. As we move into the next chapter, we will look beneath these giants. We will look into the internal structure of the planet to understand why this engine of creation eventually ran out of fuel, leaving behind a museum of stone and dust. For now, look at the horizon. Imagine the shadow of Olympus Mons stretching for 1,000 miles across the plains. Imagine the silence in the depths of Valles Marineris. These are the giants of the red planet, and they have been waiting billions of years for us to find them. To truly understand the tragedy of Mars, we cannot simply look at its surface. We must look beneath the red dust, beyond the frozen basalt, and deep into the very center of the world. We must go where the light of the sun has never reached, to the core, the mantle, and the foundation of the Martian crust. This is the internal machinery of the planet, the engine that once drove the volcanoes and generated the magnetic shield. Today, we know that this engine is quiet, but it wasn't always so. Understanding why it stopped is the key to knowing why Mars died while Earth thrived. For centuries, the interior of Mars was a realm of pure speculation. We could measure its mass and its gravity, but we couldn't hear the planet's heartbeat. That changed in 2018 with the arrival of the InSight lander. InSight wasn't a rover, it was a planetary stethoscope. It sat motionless in the Elysium Planitia, listening for Marsquakes, the tiny, subtle vibrations that ripple through the planet's interior. Through these seismic waves, we have finally been able to map the dark depths of the red planet. What we found was a world that is fundamentally different from our own, a world whose internal structure explains its rise and its eventual fall. The stethoscope on the red plains. Imagine the silence of Elysium Planitia. InSight sat there for years, deploying a sensitive seismometer called SEIS. Every time a meteor struck the planet, or the crust cracked due to cooling, or the massive weight of a volcano caused a subtle shift, a wave of energy traveled through the planet. By measuring how these waves slowed down, sped up, or reflected off different layers, scientists could see through the rock. Before InSight, many scientists thought Mars might be completely solid or have a very small, frozen core. But the data told a different story. It revealed a planet with a surprisingly large core, a sluggish mantle, and a crust that is far thicker than anyone anticipated. These layers are the chapters of Mars' biography, and they tell a tale of a world that ran out of time. The gargantuan core, a heart of iron and sulfur. At the very center of Mars lies its core. Based on InSight's data, we now know that the Martian core is surprisingly large. It has a radius of about 1,120 to 1,150 miles, 1,800 kilometers. This means the core takes up about half the radius of the entire planet. To put that in perspective, if Mars were an apple, its core would be much larger proportionally than the core of an Earth apple. But size isn't everything. Composition is what matters. The Martian core is made primarily of iron and nickel, just like Earth's, but it contains a much higher percentage of lighter elements, specifically sulfur, along with bits of oxygen, carbon, and hydrogen. This high sulfur content is crucial. Sulfur acts like an antifreeze. It keeps the iron in a liquid state at lower temperatures. And this is the first great surprise. The Martian core is still liquid. However, being liquid is not enough to generate a magnetic field. On Earth, our core has two layers, a solid inner core and a liquid outer core. The solid center grows over time, releasing heat as it solidifies. This heat drives convection, the churning, boiling motion of the liquid iron above it. This motion, combined with the planet's rotation, creates a geodynamo, a massive electrical generator that wraps Earth in a protective magnetic field. On Mars, the liquid core is remarkably uniform. Because it hasn't started to solidify at the center, there is no inner core to drive that powerful convection. The Martian engine is like a pot of water on a stove that has been turned off. The water is still liquid, but it isn't boiling. Without that churning motion, the geodynamo failed. The magnetic field, which once protected the planet, flickered and died out 4 billion years ago. The mantle, a slow-moving sea of stone. Wrapping around the core is the mantle, a thick layer of silicate rock that stands about 900 miles deep. In Earth's mantle, rock behaves like a very thick fluid over millions of years, moving in great conveyor belts that push our tectonic plates around. This constant recycling of the crust keeps Earth's surface young and helps regulate our climate. Mars, however, is a one-plate planet. Its mantle is cooler and more stagnant than Earth's. Because Mars is smaller, it lost its primordial heat much faster. Think of a small cup of coffee versus a large pot. The small cup turns cold in minutes, while the pot stays warm for an hour. Mars, the smaller world, simply cooled down too quickly. As the mantle cooled, it became more viscous, thicker, and harder to move. The plumes of heat that once fed the giant volcanoes of Tharsis grew weaker. While there may still be small pockets of warm, rising rock today, they are rare. The Martian mantle has become a silent, motionless sea of stone, no longer capable of shifting the world above it. The monolithic crust, the armor of Mars. Finally, we reach the crust, the outer shell we see as the surface. Insight revealed that the Martian crust is surprisingly thick, ranging from 15 to 45 miles deep. In some regions, it may be even thicker. Unlike Earth's crust, which is broken into dozens of moving plates that slide and crash into each other, the Martian crust is a single, solid piece. This lack of plate tectonics is why Mars has such gargantuan mountains. On Earth, a volcano can only grow so large before the plate it sits on moves away from the hotspot, cutting off its supply of lava. But on Mars, the crust stayed perfectly still. A volcano could sit over a hotspot for 1 billion years, stacking layer upon layer of lava until it pierced the sky. Olympus Mons is the monument to a crust that refused to move. But this monolithic crust also had a downside. On Earth, plate tectonics act as a planetary thermostat. We bury carbon dioxide in the crust through subduction and release it back through volcanoes, keeping our atmosphere stable. Without plate tectonics, Mars had no way to recycle its gases. Once the volcanoes stopped erupting frequently, the atmosphere had no way to replenish itself. The crust became a tomb, locking away the planet's carbon and water forever. The death of the shield, a cosmic tragedy. The most devastating moment in Martian history occurred when the internal dynamo stopped. We can see the evidence of this today in the crustal magnetism of the southern highlands. In certain ancient rocks, there are frozen magnetic signatures, ghosts of the field that once existed. These rocks tell us that 4 billion years ago, Mars had a magnetic field as strong as Earth's. When the dynamo failed, the magnetic shield vanished. Suddenly, the Martian atmosphere was defenseless. The sun, which gives life, also possesses a destructive side, the solar wind. This is a relentless stream of protons and electrons screaming away from the sun at 1,000,000 miles per hour. Without a magnetic field to deflect these particles, the solar wind slammed into the upper atmosphere. It was a process called sputtering. High-energy particles from the sun would strike a molecule of Martian oxygen or carbon dioxide and kick it out into space, like a billiard ball hitting another. Have you ever seen a comet's tail? That is the solar wind pushing gases away from the comet. For the last 4 billion years, Mars has essentially been acting like a comet, with its atmosphere constantly bleeding away into the void. NASA's MAVEN mission has measured this process in real time. Even today, Mars is losing about several pounds of its atmosphere every single second. Over billions of years, this transformed a thick, life-giving blanket into a thin, freezing veil. The atmosphere's final stand. As the air grew thinner, the planet's ability to hold onto water collapsed. We often think of boiling as something that happens with heat, but boiling is also a function of pressure. On the modern Martian surface, the air pressure is less than 1% of Earth's. If you were to stand on Mars without a pressurized suit, the water in your body, the moisture on your tongue, the fluid in your eyes, would begin to boil away, even though the temperature is freezing. This is what happened to the Martian oceans. As the pressure dropped, the water evaporated more easily. Once in the atmosphere, the sun's ultraviolet radiation broke the water molecules, H2O, apart into hydrogen and oxygen. The light hydrogen atoms escaped into space, while the oxygen atoms fell back to the surface, reacting with the iron in the soil. The planet literally rusted from the inside out. The red color we see today is the blood of the ancient Martian oceans, oxidized and scattered across the desert. The echoes in the deep. Is the heart still beating? Is Mars truly dead? The InSight mission gave us a nuanced answer. While the great geodynamo is gone, the planet isn't completely silent. InSight recorded over 1,300 Marsquakes. Some of these occurred in a region called Cerberus Fossae, a series of young fissures where the crust is still cracking. These quakes suggest that there is still some heat left in the interior. There may be pockets of magma lingering deep underground, far too deep to erupt, but warm enough to keep the rock from being totally frozen. Some scientists even speculate that this lingering internal heat could melt underground ice, creating hidden aquifers of liquid brine. If life still exists on Mars, it is likely hiding here, in the dark, warm crevices of the crust, huddled around the last embers of the planet's internal fire. The legacy of a small world. The story of the Martian interior is a story of physics and scale. Because Mars was smaller than Earth, it was destined to cool faster. Because it cooled faster, its dynamo failed. Because the dynamo failed, the shield fell. And because the shield fell, the world was stripped bare. Mars is a cautionary tale of planetary evolution. It shows us how fragile the conditions for life truly are. On Earth, we take our magnetic field and our moving continents for granted, but they are the heartbeat of our world. Mars is what happens when that heart stops beating. It is a world of incredible potential that was cut short by the cold reality of its own size. As we look at the quiet plains of Elysium, where InSight took its final breath before its solar panels were covered in dust, we shouldn't see just a dead rock. we should see a world that tried, a world that once had a heart of fire, a shield of energy, and a surface of water. The internal structure of Mars is the skeleton of a world that was once a twin to our own. In the next chapter, we will explore the Great Thinning, the specific process of how the atmosphere vanished and how the climate shifted from a tropical Noachian paradise to the frozen Hesperian desert. We will see how the loss of the heart led to the loss of the breath. For now, listen to the silence of the Martian wind. It is the sound of a planet that has finally, after 4 billion years, found peace. When we look at Mars today, we see a world that is breathtaking in its desolation. It is a world of bone-chilling cold, where the average temperature hovers around -80 degrees Fahrenheit, and the air is so thin that it would be impossible for a human to survive for even a few seconds without a pressurized suit. But as we have explored in the previous chapters, this was not always the case. Mars was once a world of thick clouds, heavy rains, and rushing rivers. The transition from that vibrant blue-green youth to this rusted, silent old age is perhaps the most dramatic transformation in the history of our solar system. This was the Great Thinning, a slow-moving catastrophe that fundamentally altered the destiny of a planet. To understand how a world loses its breath, we have to look at the invisible forces that govern the space between the planets. We have to look at the sun, the solar wind, and the delicate balance of planetary gravity. The story of Mars's atmospheric loss is not a story of a single violent impact, but a story of a billion-year-long attrition. It is a story of how a world literally bled away into the void of space. The invisible thief, the solar wind. The primary culprit in the death of the Martian atmosphere is the sun. While the sun provides the energy that allows life to exist, it also possesses a darker, more destructive side. It constantly emits the solar wind, a relentless, high-velocity stream of charged particles, mostly protons and electrons, traveling at speeds of up to 1,000,000 miles per hour. On Earth, we are protected from this onslaught by our magnetic field. Our core acts like a massive bar magnet, creating an invisible shield that deflects the solar wind around the planet, much like a rock in a stream deflects the water. But, as we learned in Chapter 4, the internal engine of Mars failed nearly 4 billion years ago. When the Martian magnetic field flickered and died, the atmosphere was left naked. Imagine the upper atmosphere of Mars as a vast, crowded room filled with molecules of carbon dioxide, nitrogen, and water vapor. Suddenly, the door is thrown open and a fire hose, the solar wind, is turned on. This is a process scientists call sputtering. When the high-energy particles of the solar wind strike the molecules in the upper atmosphere, they transfer their kinetic energy. It's like a billiard ball striking a rack of balls. Some of those molecules gain so much speed that they are kicked right out of the planet's gravitational pull and sent screaming into deep space. NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, was designed specifically to study this process. MAVEN has shown us that even today, in its weakened state, Mars is still losing its atmosphere. Every second, the solar wind strips away about 2 to 3 pounds of gas. During solar storms, when the sun is particularly active, this loss can increase by a factor of 10 or more. Over the course of 4 billion years, this slow, steady sandblasting reduced a thick Earth-like atmosphere to the thin, ghostly veil we see today. The mystery of the missing water, the isotopic fingerprint. One of the biggest questions scientists faced was, how much water did Mars actually lose? We can see the dry riverbeds and the massive deltas, suggesting a staggering amount of liquid water once existed on the surface. To find out where it went, researchers looked at the chemistry of the remaining atmosphere, specifically the ratio of hydrogen to deuterium. Hydrogen is the simplest atom in the universe, consisting of one proton and one electron. Deuterium, or heavy hydrogen, is a rare isotope that also contains a neutron. When solar radiation breaks apart a water molecule, H2O, the lighter hydrogen atoms are much easier for the solar wind to sweep away into space than the heavier deuterium atoms. By measuring the ratio of deuterium to hydrogen in the modern Martian atmosphere and comparing it to the ratio found in ancient meteorites, scientists discovered something startling. Mars has a much higher percentage of deuterium than it should. This is the smoking gun of atmospheric loss. It tells us that a massive amount of light hydrogen has escaped into space over billions of years. Based on these ratios, scientists estimate that Mars may have lost enough water to cover the entire planet in an ocean hundreds, if not thousands, of feet deep. The collapse of the greenhouse, the Great Freeze. As the atmosphere grew thinner, its ability to trap heat vanished. In its youth, the high concentration of carbon dioxide and water vapor created a powerful greenhouse effect, similar to what we see on Venus today, though much milder. This greenhouse blanket kept the surface warm enough for liquid water to exist. But as the solar winds stripped away the carbon dioxide, the planetary thermostat was turned down. The temperatures began to plummet. This created a feedback loop of cooling. As the planet grew colder, more water vapor condensed into ice and became trapped in the polar caps or buried in the ground as permafrost. Since water vapor is itself a greenhouse gas, its removal from the air caused the temperature to drop even further. This era, known as the Hesperian period, was the time of the Great Freeze. The vast oceans began to retreat. The northern sea likely froze solid before slowly evaporating away into the thinning sky. The rivers that once flowed year-round became seasonal, flowing only during brief periods of volcanic warmth or after massive asteroid impacts. Eventually, even those stopped. Mars was no longer a world of cycles. It was becoming a world of stasis. The chemistry of the Red Death. Why Mars rusted. As the atmosphere and water disappeared, the planet underwent a profound chemical transformation. This is what gave Mars its iconic crimson color. When the sun's ultraviolet radiation broke apart the water molecules in the atmosphere, it released free oxygen atoms. In a world without life to regulate the chemistry, this oxygen was incredibly reactive. It didn't form ozone or stay in the air. Instead, it combined with the iron-rich basaltic rocks on the surface. This is essentially the same process that happens to an old car left out in the rain. It rusts. The entire surface of Mars is covered in a layer of iron oxide, literally rust. This dust is incredibly fine, sometimes smaller than the particles in cigarette smoke. It permeates everything. It hangs in the thin air, giving the Martian sky its characteristic pinkish-tan hue. The red planet is a rusted world, a monument to a time when its oxygen was turned against its own crust. But this chemistry went even deeper. In recent years, Our rovers have discovered perchlorates in the Martian soil. These are salts that are toxic to humans but have a fascinating property. They lower the freezing point of water. This means that even in the freezing cold of modern Mars, highly salty brines could theoretically exist as liquids for short periods. This chemistry is the last, desperate gasp of the Martian hydrological system. The fate of the ice, the hidden reservoirs. Where is the water now? It didn't all escape into space. Much of it is still there, hidden in plain sight. The most obvious reservoirs are the polar ice caps. The northern cap is primarily made of water ice, while the southern cap is a sandwich of water ice covered by a layer of frozen carbon dioxide, or dry ice. During the Martian winter, the poles get so cold that up to 25% of the entire atmosphere freezes out onto the ground as CO2 frost. But beyond the poles, there are vast, buried glaciers in the mid-latitudes. Using ground-penetrating radar from orbit, scientists have discovered sheets of pure water ice, hundreds of feet thick, hidden under a protective layer of dust and rock. If you were to melt all the ice currently known to exist on Mars, it would be enough to cover the entire planet in an ocean over 30 feet deep. Mars isn't a dry planet, it's a frozen one. The water is still there, but it is locked in a geological prison, waiting for a heat source that hasn't existed for billions of years. Modern Mars, a world of dust and thermal stress. Today, the environment of Mars is defined by two things: extreme temperature swings and global dust storms. Because the atmosphere is so thin, it cannot hold on to heat. When the sun goes down, the temperature can drop by 100 degrees in a matter of hours. This constant cycle of heating and cooling creates immense thermal stress on the rocks, causing them to crack and shatter into the fine dust that covers the plains. This dust is the engine of the modern Martian climate. Occasionally, localized winds in a crater or a valley pick up enough dust to create a dust devil, a towering whirlwind that can reach several miles into the sky. But every few years, these small storms merge and grow, fueled by the sun's heat being absorbed by the dust itself. These storms can grow until they envelop the entire planet in a global shroud of red. During these global storms, the surface of Mars becomes a twilight world. The sun is reduced to a pale, dim blotch in the sky. For the rovers on the surface, like Spirit or Opportunity, these storms were a death sentence, covering their solar panels in dust and cutting off their power. Only nuclear-powered rovers like Curiosity and Perseverance can survive these months of darkness. The Amazonian era, the long silence. Geologists call the current era of Mars the Amazonian period. It has lasted for nearly 3 billion years. It is an era characterized by cold, dry, and slow-moving processes. While the early history of Mars was filled with fire and floods, the Amazonian is an era of wind and ice. In this period, the planet's internal heat has mostly dissipated. The volcanoes are largely dormant, though some scientists believe that eruptions could still happen every few million years. The canyons are no longer growing. The only major changes to the surface come from the occasional meteorite impact or the slow movement of the polar caps. Mars has become a museum planet. Because there is no liquid water to erode the land and no plate tectonics to recycle the crust, features that are billions of years old remain perfectly preserved. A crater formed 3 billion years ago looks almost exactly as it did the day it was created. On Earth, such a feature would be erased by rain, wind, and shifting continents in a fraction of that time. The lesson of the Great Thinning, the story of the disappearance of the Martian atmosphere, is a sobering reminder of the fragility of our own world. Mars was a planet that had everything: water, heat, and protection. But because it was small and its heart stopped beating, it couldn't hold on to its gifts. As we look at the thin, cold air of Mars today, we are seeing the end result of a cosmic battle between a planet and its star. The Sun won. It stripped away the breath of a world and turned a garden into a desert. But in doing so, it left behind a world that is uniquely suited for us to study. Mars is a laboratory where the history of the early solar system is frozen in time, waiting for us to uncover its secrets. In the next chapter, we will look at the specific places where this history is most visible, the ancient lakes of Gale and Jezero. We will see how these silent basins are providing the first real clues as to whether life ever took advantage of the Golden Age before the Great Thinning began. For now, look at the red horizon. The dust you see is the remains of a world that once was, caught in the eternal wind of a dying planet. When we talk about water on Mars, it's easy to get lost in the scale of the mega-floods or the hypothetical vastness of the Northern Ocean. But for those searching for the most profound secret of all, the secret of life, the most important stories aren't found in the roaring torrents. They are found in the quiet, still places. They are written in the fine, settled silt of ancient lake beds. On Earth, life didn't just need water, it needed stability. It needed time. It needed a place where chemistry could sit undisturbed for thousands, or even millions of years. Today, we turn our attention to the cradles of life, the silent basins of Gale and Jezero, where the ghosts of ancient Martian biology might still be hiding. The detective of Gale Crater, a mountain of history. Imagine a hole in the ground 96 miles wide. This is Gale Crater, a massive impact basin located near the Martian equator. But Gale isn't just a pit, it is a geological library. Rising from its center is a mountain nearly 3.5 miles high, Mount Sharp. When the Curiosity rover touched down in 2012, it didn't just land on a planet, it landed in the middle of a 3-billion-year-old mystery. From orbit, Mount Sharp looks like a giant layered cake. Each layer of rock represents a different epoch of Martian history. As Curiosity began its slow, agonizingly careful climb up the foothills, it was essentially traveling back in time. The mission's goal was simple but profound: to determine if Gale Crater was ever habitable. What Curiosity found changed our understanding of the red planet forever. The rover discovered mudstones, fine-grained sedimentary rocks that only form at the bottom of a lake. These weren't the result of a sudden flood. They were the product of a stable, long-lived body of water. Scientists estimate that for tens of millions of years, Gale Crater was filled with a deep, calm lake. Imagine the scene 3.5 billion years ago. You would be standing on the shore of a vast, blue lake surrounded by high crater walls. The water wouldn't be boiling or acidic. It would be fresh, much like the lakes we have on Earth. Curiosity's chemical analysis revealed that the water had a neutral pH and contained the key ingredients for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. If you were a microbe 3 billion years ago, Gale Crater was a paradise. The scent of organics, building blocks in the dust. But curiosity found something even more tantalizing. Using its internal laboratory, SAM, sample analysis at Mars, the rover cooked pinches of Martian soil and sniffed the gases that were released. In the ancient mudstones of the Murray Formation, it detected organic molecules, complex chains of carbon that are the building blocks of all known life. Now we must be careful. Organic does not necessarily mean biological. Organic molecules can be created by chemical processes in space or by the action of sunlight on minerals. But finding them preserved for 3 billion years in the Martian rock is a monumental discovery. It tells us that the raw materials for life were present. The kit was laid out on the table. All that was needed was the spark to put it together. As curiosity climbed higher, it noticed a change in the rocks. The lower layers were rich in clays, minerals that form in very wet environments. But as the rover moved upward into younger layers, it began to find more sulfates, salts that form as water evaporates. This is the physical record of the great thinning we discussed in the last chapter. Curiosity is literally driving through the death of a lake, watching as a garden turned into a salt flat. Jezero Crater, the gateway to the past. While Curiosity was exploring the library of Gale, a new mission was being prepared for an even more spectacular location, Jezero Crater. If Gale is a library, Jezero is a time capsule. Jezero is a 28-mile-wide crater that sits on the edge of a massive impact basin called Isidis Planitia. But Jezero has a feature that makes it unique in the solar system, a perfectly preserved river delta. From orbit, it is unmistakable. A river channel cuts through the crater rim and spills out into a magnificent fan-shaped structure made of layers of sand and mud. On Earth, we know that deltas are some of the most life-rich places on the planet. They act as natural traps, collecting organic material from hundreds of miles upstream and burying it in layers of protective silt. When the Perseverance rover landed in Jezero in 2021, its mission was more ambitious than Curiosity's. It wasn't just looking for habitability. It was looking for biosignatures, the actual footprints of ancient microbes. Standing in the Jezero Delta today, Perseverance sees a landscape of jagged cliffs and flat-topped buttes. These are the remnants of the delta's edges, carved away by the wind over eons. But within those layers, the rover's SHERLOC and PIXL instruments are scanning the rock at a microscopic level. They are looking for patterns, specific arrangements of minerals or chemicals that can only be explained by the presence of life. Imagine a colony of ancient Martian bacteria living in the warm, shallow waters of the Jezero Delta. As they lived and died, they might have formed stromatolites, layered mats of mineralized biology, similar to the ones we find in Australia today. If such things exist on Mars, Jezero is exactly where they would be. The river's gift, beyond the delta. The river that fed Jezero, known as Neretva Vallis, didn't just bring water, it brought geological diversity. It carried rocks from the surrounding highlands, giving Perseverance a free sample of the land far outside the crater. Among these rocks, the rover found volcanic basalts and minerals like olivine and carbonates. Carbonates are particularly exciting. On Earth, these minerals are often formed by the shells of sea creatures, or by the chemical interaction between an ocean and a carbon-rich atmosphere. In Jezero, these carbonates might have acted like a trap for ancient organic matter, sealing it away from the destructive radiation of the Martian surface. But Perseverance isn't just analyzing these rocks, it is collecting them. The rover is equipped with a complex sampling system that drills into the most promising rocks and seals the cores in titanium tubes. These tubes are being left on the surface, waiting for a future mission to pick them up and bring them back to Earth. This is the Mars Sample Return Mission, perhaps the most complex robotic undertaking in history. When those samples finally arrive in a laboratory on Earth, we will be able to apply the full power of our most advanced technology to answer the question once and for all. Were we ever alone? Other basins. The forgotten lakes of Mars. Gale and Jezero are the stars of the show, but they are not the only places where water once pooled. Consider Gusev Crater, where the Spirit rover landed in 2004. Initially, Spirit was disappointed. The floor of the crater was covered in boring volcanic basalt. But when the rover climbed into the nearby Columbia Hills, it found something incredible: evidence of ancient hot springs. It found deposits of pure silica that, on Earth, are only found around hydrothermal vents, places where hot, mineral-rich water bubbles up from the ground. These are some of the most likely places for life to begin. Spirit showed us that Mars didn't just have cold lakes, it had hot spots of energy and chemistry. Then there is the Iridania Basin in the southern highlands. This was once a massive inland sea, much larger than the Caspian Sea on Earth. Scientists believe that at the bottom of the Iridania Sea, there were hydrothermal vents deep underwater. This is fascinating because many biologists believe that life on Earth didn't start in a shallow pond, but in the dark, high-pressure environment of the deep ocean floor. If that's true, the Iridania Basin might be the true birthplace of Martian life. The stability of the silent basins. Why do these lakes matter so much more than the massive outflow channels? It comes down to residence time. In an outflow channel, the water moves so fast and disappears so quickly that life doesn't have a chance to take hold. It's like trying to build a city in the middle of a hurricane. But in a crater like Gale or Jezero, the water was there for millions of years. This allowed for cycles of evaporation and replenishment. It allowed for different chemical environments to form at different depths. It allowed for a stable temperature. Most importantly, it allowed for concentration. Life requires chemicals to be close enough to each other to interact. In a calm lake, minerals and organics can settle and concentrate in the mud, creating the primordial soup that we talk about in biology. The concept of habitability, a multi-stage test. When scientists talk about habitability, they are looking for three things. 1. Liquid water. We know Gale and Jezero had it. 2. The right chemicals. We've found the building blocks. 3. An energy source. On Mars, this could be the sun or the internal heat of the planet. Mars passed all three tests. For at least 1 billion years, the red planet was habitable. This doesn't mean life was there, but it means the door was open. If life didn't start on Mars, we have to ask ourselves why. What does Earth have that Mars didn't? Or perhaps is life much harder to start than we think? The preservation of the past. The irony of Mars is that its death as a living planet is what makes it so valuable as a scientific one. On Earth, plate tectonics and a powerful water cycle have erased almost all evidence of our earliest history. We have very few rocks from 4 billion years ago, and those we do have are mangled and melted by the heat of the crust. But on Mars, there is no recycling. The cradles of life have been sitting in the cold, dry air for 3 billion years, perfectly preserved. The deltas haven't been washed away. The mudstones haven't been crushed into the mantle. Mars is a time machine. By studying the ancient lakes of Mars, we are effectively studying the prehistory of our own world. We are looking at the conditions that existed right before life took over the Earth. The search continues. As curiosity continues to climb Mount Sharp and perseverance explores the higher reaches of the Jezero Delta, we are getting closer to the truth. We are finding more complex organics. We are finding more evidence of stable water. Each drill hole is a new sentence in the biography of the Red Planet. The story of the Martian lakes is a story of patience. The water was patient, sitting in those basins for eons. The rocks were patient, holding onto their secrets for billions of years. And now, we must be patient. We are looking for something very small, a microscopic signature in a desert of red dust. But if we find it, it will be the greatest discovery in the history of our species. In the next chapter, we will leave the quiet basins and look at the modern explorers, the machines and the people who have dedicated their lives to uncovering these secrets. We will look at the history of our missions, from the first grainy photos of Viking to the helicopter flights of Ingenuity. For now, look at the dry fans of Jezero. Imagine them as they once were, lush, wet, and potentially teeming with the very first breaths of a second world. The history of Mars exploration is not merely a timeline of rockets and circuit boards. It is a long, patient, and often heartbreaking conversation between a curious species and a silent, ancient world. For decades, we have been knocking on the door of the Red Planet. Each mission we send is a question whispered into the void, and every image or data point sent back is an answer that has traveled millions of miles across the cold silence of space. From the first grainy black and white snapshots to the high-definition drone footage of today, our robotic emissaries have transformed Mars from a distant, fuzzy light in the sky into a place we can almost touch. Today, we tell the story of the modern explorers, the machines that became our eyes, our hands, and our heart on another world. The Great Silence and the First Knock. Before 1965, Mars was a world of pure imagination. Astronomers like Percival Lowell had peered through telescopes and seen what they thought were canals, fueling a century of science fiction about advanced civilizations and dying empires. But when the Mariner 4 probe flew past the planet in 1965, the dream of a lush, populated Mars died instantly. The 21 photos it sent back showed a cratered, moon-like desert. It was a cold, dead place. But humanity didn't give up. If there were no canals, what was there? In 1976, we decided to land. The Viking 1 and Viking 2 missions were the most ambitious scientific undertakings of their time. Imagine the suspense in the control room at NASA as the first lander descended. There were no high-speed internet links or real-time video feeds. There was only a series of beeps and telemetry data. When the first image finally formed on the screens, one pixelated line at a time, it revealed something breathtaking. It showed a landscape of rocks and orange dust stretching to a pink horizon. It was the first time human eyes had seen the surface of another planet from the ground. The Vikings weren't just photographers, they were biologists. They were equipped with miniature laboratories designed to search for the chemical footprints of life. The results were agonizingly ambiguous. One experiment suggested metabolic activity, while another found no organic molecules. The scientific community was split, and for a long time, the mystery of Martian life was shelved. But the Vikings had done something more important. They had proved that Mars was a physical, tangible world, with weather, seasons, and a history waiting to be read. The Mapmaker. Seeing the giants in high definition. After the Vikings, there was a long silence, a 20-year gap where our attempts to return were met with failure and lost signals. But in 1996, the silence was broken by the arrival of Mars Global Surveyor. If the Vikings showed us a backyard, Global Surveyor showed us the entire estate. For nearly a decade, this orbiter circled the planet, using a laser altimeter to map every mountain, canyon, and crater with incredible precision. This was how we truly discovered the scale of the giants we discussed in Chapter 3. We saw the true height of Olympus Mons and the terrifying depth of Valles Marineris. We saw features that looked like ancient shorelines and dry riverbeds. Global Surveyor turned Mars from a collection of landing sites into a global map, allowing us to see the planet as a complex, evolving system. The little rovers that could, Spirit and Opportunity. In 2004, the exploration of Mars became personal. This was the era of the Mars exploration rovers, Spirit and Opportunity. These weren't stationary landers, they were six-wheeled robotic geologists, roughly the size of a golf cart. Their mission followed a simple, powerful philosophy. Follow the water. The landings themselves were a masterpiece of engineering. Because the Martian atmosphere is too thin for parachutes alone, but too thick to ignore, the rovers were encased in a giant cluster of airbags. They literally bounced and rolled across the Martian plains like cosmic beach balls before coming to a stop. Spirit landed in Gusev Crater, while Opportunity landed on the other side of the planet in Meridiani Planum. They were designed to last for only 90 days. Instead, they became legends. Opportunity, in particular, spent 15 years wandering the plains. It found the blueberries, tiny spheres of hematite that prove liquid water once soaked the ground. It explored massive craters like Victoria and Endeavour, looking into the deep history of the Martian crust. Spirit, despite getting stuck in a sand trap, discovered evidence of ancient hot springs, the first indication that Mars once had hydrothermal energy. These rovers captured the public's imagination like no other mission. They felt alive. When Opportunity finally felt silent in 2018 during a global dust storm, its last message, "My battery is low and it's getting dark," sent a wave of genuine grief through millions of people back on Earth. They were no longer just machines. They were our scouts, brave and persistent, until the very end. 7 minutes of terror. The arrival of curiosity. By 2012, we were ready for something bigger, much bigger. Curiosity, the Mars Science Laboratory, was the size of a small SUV and weighed nearly a ton. It was too heavy for airbags. To land it, NASA engineers had to invent something that sounded like science fiction, the sky crane. The landing sequence was famously dubbed the 7 Minutes of Terror. The spacecraft had to slam into the atmosphere at 13,000 miles per hour, deploy a massive parachute, then detach a rocket-powered backpack that would hover over the surface and gently lower the rover on nylon tether lines before flying away. There was no room for error. If a single sensor failed, the billion-dollar mission would become a new crater. The sky crane worked perfectly. Curiosity landed in Gale Crater, and its mission represented a shift in focus. We were no longer just looking for water. We were looking for habitability. As we discussed in Chapter 6, Curiosity's drill and internal laboratory confirmed that Gale Crater was once a freshwater lake that could have supported life. Curiosity transformed our understanding of Mars from a dead desert into a former home. Even today, over a decade later, Curiosity is still climbing Mount Sharp, sending back high-resolution panoramas that look so much like the American Southwest that it's easy to forget they were taken on another world. Feeling the pulse, the silence of insight. In 2018, we sent a different kind of explorer. While the rovers were busy looking at the surface, InSight was designed to look down. This stationary lander was a planetary cardiologist. It carried a seismometer so sensitive that it could detect vibrations smaller than the width of a hydrogen atom. InSight's journey was a quiet one. It sat in the Elysium Planitia for 4 years, listening to the Mars quakes. It was through InSight that we finally mapped the interior of the planet, as we explored in Chapter 4. We learned about the oversized liquid core and the thick, monolithic crust. InSight taught us that while Mars may be geologically quiet, it is not yet dead. There is still heat, still movement, and still mystery hidden in the deep. The dream team? Perseverance and ingenuity. In February 2021, the most advanced mission yet arrived at Jezero Crater. The Perseverance rover and its tiny companion, the Ingenuity helicopter. Perseverance, or Percy, is a twin to Curiosity, but with a much more difficult job. It is a sample collector. Its mission is to identify the most scientifically valuable rocks, those that might hold ancient biosignatures, and drill out small cores to be cached for a future return to Earth. Perseverance is the first step in a multi-decade relay race to bring a piece of Mars back to our laboratories. But it was Ingenuity, a small 4-pound drone, that stole the show. The Martian atmosphere is 1% the density of Earth's. Flying there is equivalent to flying at an altitude of 100,000 feet on Earth. Many experts thought it was impossible. But on April 19, 2021, Ingenuity spun its blades at 2,400 RPM and lifted off. It was a Wright brothers moment on another world. Ingenuity was only supposed to fly 5 times. It flew over 70 times. It became an aerial scout for Perseverance, flying ahead to spot obstacles and find the best paths through the Jezero Delta. It proved that the Martian sky is not a barrier, but a new frontier for exploration. The human element, the scientists behind the screens. When we talk about these explorers, we often forget the thousands of people who operate them. There is a whole community of scientists and engineers who live on Mars time. Because a Martian day, a sol, is 40 minutes longer than an Earth day, their schedules constantly shift. They wake up in the middle of the night to send commands to the rovers and spend their days debating which rock to drill or which crater to explore, there is an emotional weight to this work. These people spend years, sometimes decades, working on a single instrument. When a rover like Opportunity dies, it's not just a technical failure. It's the end of a career's worth of effort. Their passion is the fuel that keeps these machines moving across the red dust. Why do we go? Looking back at the path from Viking to Perseverance, we have to ask, why do we keep going? Why spend billions of dollars on a cold, dry rock? The answer lies in our nature as explorers. Mars is the only other world in the solar system where humans could theoretically stand on the surface and see a landscape that feels familiar. It is the ultimate mirror for Earth. By studying Mars, we learn about the fragility of our own atmosphere, the history of our own climate, and the potential for life to exist throughout the universe. Every mission we send is a bridge. We are building the infrastructure of knowledge that will one day allow humans to follow in the footsteps of the rovers. We have moved from observing Mars through a glass lens to touching its soil with robotic hands. The bridge to the future. As we speak, the orbiters above Mars are acting as a communications network, a Martian internet that connects our explorers to Earth. They are monitoring the weather, tracking the dust storms, and searching for the best places for the next generation of landers. The story of the modern explorers is far from over. Even as Perseverance drills into the Jezero Delta and Curiosity climbs the heights of Mount Sharp, new missions are on the drawing boards. We are planning the Mars sample return. We are looking at the moons Phobos and Deimos. And we are dreaming of the day when the first boot print is pressed into the red dust. In the next chapter, we will shift from the reality of science to the power of the mind. We will explore the riddles of Mars, the faces, the pyramids, and the illusions that have haunted our imagination and forced us to confront the boundary between geology and mythology. For now, listen to the hum of the rovers. They are the heralds of a new era, the pioneers of a world that is no longer a stranger, but a neighbor we are finally getting to know. Mars has always been more than just a planet to humanity. It has been a canvas. For as long as we have been able to look at that tiny red spark in the night sky, we have projected our deepest hopes, our most primal fears, and our wildest imaginations onto its surface. Long before the first robotic explorers touched its dust, there existed a Mars of the mind, a world of vast canal systems, dying ancient civilizations, and silent, abandoned cities. These ideas didn't just come from science fiction, they came from the very limits of our vision. Today, we explore the riddles of Mars, the faces, the pyramids, and the geometric illusions that have haunted our collective consciousness and forced us to confront the boundary between objective geology and the subjective power of the human brain. The face that launched 1,000 theories. The most famous riddle in the history of space exploration began on July 25, 1976. The Viking 1 orbiter was circling the planet, scouting for a landing site for its sister craft, Viking 2. As it flew over a region known as Cydonia, it snapped a series of images of the rugged, mesa-filled landscape. When the data reached Earth, one image stood out, frame 35A72. There, sitting in the middle of a desert plain, was a massive rock formation that looked unmistakably like a human face. It had eyes, a nose, a mouth, and even a strange helmet-like headdress. NASA released the image with a cautious caption, noting that it was a huge rock formation, which resembles a human head. But the caution of scientists was no match for the hunger of the public imagination. Suddenly, Mars wasn't just a dead rock. It was a graveyard of giants. Books were written, documentaries were produced, and a generation of believers argued that the face on Mars was a monument built by an extinct civilization, perhaps a warning to us, or a memorial to a lost world. This single image changed the cultural trajectory of Mars exploration for 20 years. It turned the Cydonia region into a holy site for those searching for proof that we are not alone. The psychology of the unknown. Pareidolia. To understand why the face had such a grip on us, we have to look inward at the biology of the human brain. We are social creatures, and our survival has always depended on our ability to recognize faces instantly. This phenomenon is called pareidolia. It is the reason you see a man in the moon, a dragon in a cloud, or a smiling face in an electrical outlet. Our brains are hardwired to find patterns in chaos. When the Viking 1 orbiter took that photo, the sun was at a very low angle, casting long, dramatic shadows across the Martian mesas. The combination of low resolution and the play of light and shadow created a perfect inkblot test for humanity. We saw a face because we wanted to see a face. We projected our own image onto the red dust of another world. As technology improved, the riddle began to unravel. In 1998, the Mars Global Surveyor returned to Cydonia with cameras that were far more powerful than those of the 1970s. When it photographed the face again, the headdress, the eyes, and the mouth vanished. What remained was a mesa, a flat-topped hill common in the American Southwest. It was a beautiful geological feature, carved by wind and ancient water, but it was just a rock. Later, the Mars Reconnaissance Orbiter provided images so sharp that you could see individual boulders on the slopes. The face was officially dead, replaced by a complex, weathered landform. Yet, the myth persists, proving that the human heart is often more powerful than the scientific lens. The Pyramids of Cydonia. Geometry versus geology. The face was not alone. Near the famous mesa, researchers pointed to other structures that appeared to have perfect geometric symmetry. These were the Pyramids of Cydonia, massive five-sided structures that seemed too regular to be natural. Some argued that they were arranged in a pattern that mirrored the pyramids of Giza or the stars in Orion's belt. But geology has a way of mimicking geometry in spectacular ways. On Earth, we have yardangs, long streamlined ridges carved by persistent winds. We have pyramidal peaks in the Alps and the Himalayas, formed by the intersection of multiple glaciers. On Mars, the combination of basaltic rock layers and billions of years of wind erosion can create incredibly sharp, angular shapes. Basalt often breaks in straight lines at 90-degree angles, a process called columnar jointing. When the fierce Martian winds sandblast these rocks for eons, they can carve out mesas that look like fortresses and hills that look like pyramids. The city of Cydonia turned out to be a collection of natural landforms, but its existence forced us to look closer at the power of Martian erosion. It taught us that on a world without plate tectonics, the wind is the master architect, capable of creating monuments that look eerily intentional. The little mirages, from blueberries to roots. The riddles of Mars aren't always on a grand planetary scale. Since we landed our rovers, we have encountered smaller illusions that have sparked just as much debate. The Opportunity rover found what looked like thousands of tiny, silver-grey blueberries scattered across the ground. For a brief moment, people wondered if they were fossils or eggs. In reality, they were concretions, small spheres of hematite that formed inside wet rocks billions of years ago. More recently, the Curiosity and Perseverance rovers have sent back images of rocks that look like tortoise shells, thigh bones, or even tangled plant roots. On the internet, these images go viral instantly as proof of life. But every time, the explanation is more grounded. Mars is a world of extreme thermal stress. Rocks freeze and thaw, expanding and contracting until they crack in patterns that look like biology. Wind-blown sand polishes stones into shapes that mimic bones or tools. We are seeing the art of the desert, a gallery of stone created by the relentless patience of the wind. The mystery of the dark streaks. RSL. Not every riddle on Mars is an illusion of the mind. Some are genuine scientific mysteries that are still being debated today. One of the most fascinating is the recurrent slope lineae, or RSL. These are dark, narrow streaks that appear on steep Martian slopes during the warm seasons. They grow slowly downward, then fade away in the warm seasons. They grow slowly downward, then fade away in the winter, only to reappear the next year in the same spot. When they were first discovered, the scientific world was ecstatic. They looked exactly like seeps of liquid water, briny streams flowing just beneath the surface. But as we studied them closer, the mystery deepened. Orbital spectrometers struggled to find a clear signature of water. New theories suggested they might be dry grain flows, cascades of dark sand triggered by the heating of the soil. However, the way they grow and fade still behaves very much like a liquid. The RSL remain one of the most tantalizing maybe stories on Mars. They are a reminder that even after 50 years of study, the planet still has the power to surprise and baffle us. Polygons and honeycombs. The geometry of ice. In the high latitudes of Mars, the ground itself takes on a strange geometric pattern. It looks like a giant honeycomb or a series of interconnected polygons stretching for hundreds of miles. To an untrained eye, it looks like a paved road system or an ancient city grid. But this is the breath of the frost. On Earth, we see the same patterns in the Arctic and Antarctic. As the ground freezes and thaws, the ice beneath the surface expands and contracts, pushing the soil into regular geometric shapes. On Mars, where the permafrost layer is global and massive, this process happens on a scale that is staggering. The honeycombs are the fingerprints of a planet that is still thermally active, a world where ice is the primary sculptor of the plains, the ghostly eye of Hellas. Even the great giants have their riddles. As we mentioned in Chapter 3, the Hellas Basin often fills with a thick white fog. From space, it can look like a solid white disk, a ghostly eye looking back at Earth. Early astronomers thought it might be a polar cap or even a cloud of smoke from an industrial civilization. Today, we know it is a combination of dust and carbon dioxide frost. Because Hellas is so deep, the air is thicker there, allowing frost to form more easily than on the surrounding plateaus. But the sight of that massive, pale circle in the southern hemisphere continues to inspire a sense of wonder. It is a reminder that Mars is a world of atmospheric theatre, where the air itself can create illusions of solid ground. Why the riddles matter. It is easy to dismiss the face on Mars or the pyramids as mere curiosities or the products of overactive imaginations. But these riddles have played a vital role in our exploration. The public fascination with Cydonia provided the political and cultural momentum to keep sending missions to Mars when the science budget was under threat. More importantly, these illusions force us to be better scientists. They teach us to question our first impressions. They remind us that to find the truth, we must look past the face and see the geology. They challenge us to understand the extreme environments of Mars, how wind, ice, and radiation can create forms that mimic life. Every time we debunk a Martian riddle, we replace a myth with a fact that is often even more incredible. A face is just a hill, but that hill is a 3-billion-year-old record of a time when Mars was a different world. A pyramid is just a mesa, but its sharp edges tell us about the power of the Martian wind. The ultimate riddle, the habitable silence. The greatest riddle of Mars is not a rock or a shadow. It is the silence itself. As we have seen, Mars has everything it needs to support life. It has water in the past and as ice today. It has energy and it has the right chemicals. So, where is everybody? The fact that we see faces and cities in the dust is a reflection of our loneliness. We are a species that desperately wants to find a neighbor. We look at Mars and we don't see a desert. We see a mirror. We want to know if the same processes that created us happened elsewhere. The riddles of Mars are the questions we ask the universe, and so far, the universe has responded with a beautiful, complex, but profoundly quiet geology. The canvas remains. As we move into the next chapter, we will leave the illusions behind and look at the moons of Mars, Phobos and Deimos. These tiny, irregular satellites have their own mysteries, including monoliths and grooves that have sparked their own share of legends. Mars will always be a place of riddles. As long as there are shadows on its mesas and dust in its air, we will see things that aren't there. And that is a good thing. It is the imagination that drives the science. We go to Mars because we want to know the truth, but we dream of Mars because we want to find ourselves. For now, look at the Cydonia plains as the sun sets. The shadows grow long, and for a moment, the hills might look like faces again. But now you know the secret. The real face of Mars is the one hidden in its rocks, its ice, and its billion-year history of change. High above the rusted plains and the silent volcanoes of Mars, two tiny, irregular shadows dance across the sky. They are not the grand, luminous orbs like our moon. They are small, lumpy, and battered, looking more like cosmic debris than planetary satellites. Their names are Phobos and Deimos, or fear and dread, named after the sons of the Greek god of war who accompanied their father into battle. For decades, these two moons have remained among the most enigmatic objects in our solar system. Despite their modest size, they hold the keys to understanding the violent history of the Martian system and the inevitable destructive future that awaits them. Today, we explore the sentinels of fear, the moons that shouldn't be there, and the tragic fate that will one day tear them apart. The inner demon, the doom of Phobos. If you were standing on the surface of Mars looking west, you would see something that defies the logic of every other moon in the solar system. Phobos, the larger and closer of the two satellites, doesn't rise in the east like our moon. Instead, it screams across the sky from west to east, crossing the horizon in just over 4 hours. It moves so fast that it completes nearly 3 full orbits around Mars in a single Martian day. This frantic pace is a symptom of a dangerous intimacy. Phobos orbits Mars at a staggeringly low altitude, just 3,700 miles, 6,000 kilometers above the surface. To put that in perspective, our moon is nearly 240,000 miles away from Earth. Phobos is so close that it is practically skimming the atmosphere. But this closeness comes at a terrible price. Phobos is locked in a death spiral. Because it orbits faster than the planet rotates, Martian gravity is constantly tugging at it, acting like a brake. Every century, Phobos drops about 6 feet, 2 meters, closer to the surface. It is a slow, agonizing descent that has been happening for billions of years, and the countdown is reaching its final chapters. The grooves of destruction, a moon under stress. When we look at high-resolution images of Phobos, we see a world that is literally falling apart. The surface is covered in long, parallel grooves or stretch marks. For years, scientists thought these were scars from the massive impact that created the Stickney crater, the giant hole that makes Phobos look like the Death Star. But recently, a more terrifying theory has emerged. These grooves are likely tidal stretch marks. As Phobos gets closer to Mars, the planet's massive gravitational pull is stretching the moon like a piece of taffy. Because Phobos isn't a solid block of rock, but rather a rubble pile, a loose collection of boulders and dust held together by gravity, it cannot withstand this internal tension. The grooves are the cracks forming in its foundation. The moon is being torn apart from the inside out, millions of years before it even touches the atmosphere. Scientists estimate that in 30 to 50 million years, a mere blink in cosmic time, Phobos will reach the Roche limit. This is the point where the gravity of Mars becomes stronger than the gravity holding Phobos together. In a spectacular and violent event, Phobos will shatter. Billions of tons of rock and dust will be scattered into orbit, and for a few million years, Mars will become a ringed planet, sporting a thin crimson halo of debris before the fragments eventually rain down on the surface as a final catastrophic meteor shower. Stickney, the impact that almost ended everything. We cannot talk about Phobos without mentioning Stickney crater. Taking up nearly half the width of the moon, this crater is the result of a collision so powerful that it nearly shattered Phobos into dust billions of years ago. The object that struck it must have been several hundred meters wide, hitting with the force of 1 million nuclear bombs. The impact was so violent that it sent shockwaves through the entire body of the moon, echoing back and forth until the rock was pulverized into a fine, powdery regolith. Today, the floor of Stickney is covered in a layer of dust hundreds of feet deep. If a future astronaut were to step into the crater, they might find themselves sinking as if in quicksand, a silent, airless trap on the edge of the abyss. Deimos, the drifting ghost. Far beyond the frantic orbit of Phobos lies its smaller sibling, Deimos. While Phobos is a world of drama and destruction, Deimos is a world of slow, ghostly stillness. It is significantly smaller, only about 7 miles wide, and sits at a much safer distance of 14,000 miles. Unlike Phobos, Deimos is moving away from Mars. Because it orbits slower than the planet rotates, the gravitational interaction is pushing it further into the void, much like our own moon is slowly drifting away from Earth. From the surface of Mars, Deimos looks like a bright, steady star that takes over 2 days to cross the sky. Deimos is also remarkably smooth. While Phobos is jagged and grooved, Deimos appears pillowy. Its craters are filled with a thick layer of fine dust that has settled over billions of years, smoothing out the rough edges. It is a world in deep hibernation, a silent witness to the chaos happening just a few thousand miles beneath it. The great mystery, captured or created. The existence of these two moons is one of the greatest riddles in planetary science. They don't look like they belong to Mars. They are dark, carbon-rich objects that look exactly like D-type asteroids found in the outer asteroid belt. For decades, the leading theory was that Phobos and Deimos were stray asteroids that wandered too close to Mars and were snatched by its gravity. But there is a problem with the capture theory: their orbits. If they were captured, their orbits should be elongated and tilted. Instead, they are nearly perfect circles aligned with the Martian equator. This is almost impossible to achieve through random capture. This has led to the giant impact hypothesis. Many scientists now believe that billions of years ago, a massive object, perhaps the size of a dwarf planet, slammed into Mars. The collision would have ejected a colossal disk of debris into orbit. Over time, that debris coalesced to form several moons. Most of them would have been large and would have eventually crashed back into the planet. But Phobos and Deimos are the last two survivors of that ancient, violent ring. By studying these moons, we are effectively studying the debris of the impact that created the modern Mars. The MMX mission, touching the void. To solve this riddle, we are preparing to go there. The Japan Aerospace Exploration Agency, JAXA, is currently developing the Martian Moon's Exploration MMX mission. Set to launch in the mid-2020s, MMX will do what no other mission has done. It will land on Phobos, collect a sample of its dust, and bring it back to Earth. This mission is crucial because Phobos is effectively a delivery service for Martian history. For billions of years, every time an asteroid hit Mars, bits of the Martian surface were blasted into space. Much of that dust landed on Phobos. By sampling the surface of this moon, we might find pieces of the ancient, wet Mars that were preserved in the cold vacuum of space, far away from the erosive winds of the planet below. 2010 will tell us if these moons are truly captured asteroids or the offspring of a planetary cataclysm. Phobos and Deimos as a bridge to the future. Beyond the science, these moons hold immense strategic value. Because they have almost no gravity, landing on them is more like docking with a space station than landing on a planet. They could serve as perfect staging grounds for future human missions. Imagine a base on the Mars-facing side of Phobos. Because the moon is tidally locked, meaning the same side always faces the planet, the view would be breathtaking. Mars would fill nearly half the sky, a massive rusted marble hanging permanently overhead. From such a base, astronauts could operate rovers on the surface in real time, with no signal delay. The moons could be used as fuel depots, shielding crews from radiation while they prepare for the final descent to the Red Planet. The Sentinel's final watch. Phobos and Deimos are reminders that in the cosmos, nothing is static. One moon is being pulled into a final fiery embrace with its parent, while the other is slowly waving goodbye. They are the leftovers of a forgotten era, guardians of a world that once had oceans and now has only dust. As we look at the lumpy, battered faces of these two moons, we see the scars of billions of years of cosmic history. They have watched the volcanoes grow silent. They have seen the oceans evaporate. They have witnessed the great thinning. And through their silent orbits, they continue to offer us clues to the origin of our neighbor. In the next chapter, we will return to the surface of Mars, but we will look toward the horizon. We will explore Mars in the near future. The realistic expectations of what we will find in the next 20 years, the technologies we are building to survive there, and the cold reality of what it means for a human to step into the red dust. For now, watch the two shadows as they cross the Martian night. One is falling, one is drifting, and both are waiting for us to finally reach out and touch them. We stand today at a strange crossroads in our history with the red planet. For the first time, Mars is no longer a distant point of light or a grainy image on a computer screen. It is a world we have mapped, measured, and touched with our robotic hands. We talk of colonization and multi-planetary species as if these were inevitable milestones on a calendar. But as we look toward the next 30 years, we must separate the soaring rhetoric of visionaries from the cold, hard physics of deep space. The future of Mars is not a fast-paced cinematic montage. It is a long, grueling, and incredibly expensive marathon. Today, we explore the red horizon, the realistic expectations, the looming technological hurdles, and the quiet, steady work that will define our next steps onto the Martian dust. The Holy Grail, the great relay race of sample return. Before a single human boot touches the Martian regolith, we must solve a problem that has baffled engineers for half a century. How do we bring Mars back to Earth? This is the Mars Sample Return (MSR) program, a joint venture between NASA and the European Space Agency, ESA. It is, without hyperbole, the most complex robotic endeavor ever conceived. Currently, the Perseverance rover is busy filling small titanium tubes with cores of Martian rock from the Jezero Delta. These tubes are the holy grail of planetary science, but they are currently sitting on the floor of a crater 140 million miles away. Bringing them home requires a logistical triple jump that has never been attempted. First, a lander must touch down near the cache, an incredible feat of precision landing. Then, a small fetch rover or a pair of helicopters must retrieve the samples. Next comes the hardest part, the Mars Ascent Vehicle, MAV. This is a small rocket that must survive the journey to Mars, wait for months in the freezing dust, and then successfully launch from the surface. The first rocket ever to take off from another planet. Once in orbit, the MAV must perform an autonomous handshake with an ESA-built orbiter, which will then begin the long journey back to Earth. This isn't just a technical challenge, it's a biological one. We have to ensure planetary protection. We must guarantee that no Martian microbes, if they exist, escape into Earth's biosphere, and conversely that we don't contaminate the samples with Earth life. The cost of this program is measured in billions, and the timeline stretches into the late 2030s. But until we have those rocks in our laboratories, where we can use instruments 1,000 times more powerful than anything we can send on a rover, the true history of life on Mars will remain a mystery. The invisible killer, The radiation wall. When we talk about sending humans to Mars, we often focus on the rocket, the massive boosters and the sleek habitats. But the greatest threat to a Martian pioneer is invisible. It is the radiation environment. On Earth, we are shielded by a massive atmosphere and a powerful magnetic field. On Mars, as we've learned, both are effectively gone. A trip to Mars is a 9-month bath in high-energy particles. There are two main types: solar energetic particles, SEP, from the Sun, and galactic cosmic rays, GCR, from deep space. While we can shield against solar flares with thick layers of water or lead, GCRs are like microscopic bullets traveling near the speed of light. They can pass through the hull of a ship, through the walls of a habitat, and directly through human DNA. Data from the Curiosity rover and the InSight lander show that the radiation on the Martian surface is about 2.5 times higher than what astronauts experience on the International Space Station, and hundreds of times higher than on Earth. A 3-year mission to Mars, the minimum time for a round trip, would push an astronaut to the very limit of acceptable lifetime radiation exposure. How do we solve this? Some suggest building habitats underground or inside lava tubes, the ancient, hollowed-out volcanic tunnels we discussed in earlier chapters. These natural fortresses could provide meters of solid rock shielding. But building a base inside a cave on another world presents its own nightmare of engineering and psychological stress. Until we develop new materials or faster propulsion systems that shorten the journey, radiation remains the hard ceiling of human exploration. Breathing from the stone, the magic of Isru. To live on Mars, we cannot bring everything with us. A single gallon of water weighs 8 pounds. A tank of oxygen weighs hundreds. To make Mars sustainable, we must learn the art of in situ resource utilization, or ISRU, living off the land. We have already taken the first step. The MOXIE experiment on the Perseverance rover proved that we can inhale the thin Martian CO2 and exhale pure, breathable oxygen. It's a mechanical tree. But MOXIE was just a pilot. To support a crew, we need a version 100 times larger, running on a nuclear power source. Water is the next target. We know there is ice, billions of tons of it, buried just beneath the dust. But Martian ice is not like the ice in your freezer. It is mixed with a harsh, salty soil containing perchlorates, chemicals that are toxic to human thyroids. To get a drink of water, a Martian colonist will have to be a master chemist, mining frozen dirt, melting it, and purifying it through a complex series of filters. The technology to do this at scale doesn't exist yet. It is currently in the stage of laboratory prototypes and simulated Martian dirt in desert test sites. The methane mystery. Biology or geology? While we prepare for humans, our robots are chasing a ghost, methane. On Earth, the vast majority of methane is produced by life, cows, swamps, and bacteria. Curiosity has detected puffs of methane in Gale Crater that seem to rise and fall with the seasons. Is this the burp of ancient microbes living deep underground, warmed by the planet's remaining internal heat? Or is it serpentinization, a purely geological process where water reacts with olivine rocks? We don't know. The Trace Gas Orbiter, TGO, has searched for this methane from above and, strangely, found almost nothing. This methane paradox is one of the most frustrating and exciting puzzles in modern science. If we find that the methane is biological, it changes everything. It means Mars is not a museum. It is an active, living ecosystem, But for now, it remains a whisper in the wind. The terraforming myth, a cold reality check. No discussion of the Martian future is complete without the dream of terraforming, turning the red planet into a second Earth. The idea is simple in theory. Melt the polar caps, release the CO2, create a greenhouse effect, and let the water flow. But a 2018 study backed by NASA delivered a devastating reality check. There simply isn't enough CO2. Even if we could vaporize every ounce of frozen gas on the planet, the atmospheric pressure would only rise to about 7% of Earth's. You still couldn't breathe, and the water would still boil away. To truly terraform Mars, we would need to import gases from the outer solar system, diverting comets or moving moons, a feat of engineering that is centuries, if not millennia, beyond our current reach. For the foreseeable future, life on Mars means life in a pressurized bubble. It means living in a suit. It means seeing the sky through a reinforced window. Mars is not Earth 2.0. It is a hostile, beautiful, and unforgiving frontier that will demand every ounce of our ingenuity just to keep us alive for a single day. The quiet marathon. So, what is the realistic timeline? We are looking at the 2030s for the return of the first samples. We are looking at the 2040s or 2050s for the first human orbit-only missions or a brief flag and footprints landing. A permanent base is likely a project for the late 21st century. This is not a story of a sudden breakthrough. It is the story of a long, quiet marathon. It is the story of engineers at NASA, ESA, and private companies like SpaceX, arguing over valve designs and heat shields. It is the story of scientists analyzing every grain of dust to ensure our machines don't fail. Mars is hard. It is the hardest thing our species has ever tried to do. But that is why we do it. Mars forces us to innovate. The technologies we develop to recycle water on Mars will save lives in drought-stricken areas on Earth. The solar panels and nuclear batteries we build for the Martian night will revolutionize our energy grid at home. As we look towards the red horizon, we see a planet that is slowly waking up, not geologically, but in our consciousness. Every rover that lands, every helicopter that flies, and every sample that is cached is a bridge to the future. Mars is a mirror. It shows us what happens to a planet when things go wrong, and it challenges us to see if we have the wisdom to make things go right. It is a lonely, cold, and quiet world, but it is waiting. It has been waiting for 4 billion years for someone to come back and listen to its story. In our final chapters, we will summarize this incredible journey and look at the Mars of the mind, the philosophical and cultural legacy of the Red Planet. We will reflect on what it means for us to be the generation that finally decoded the secrets of another world. For now, the wind continues to blow across the Jezero Delta. The dust settles on the solar panels of silent landers, and somewhere, 140 million miles away, a robotic arm is carefully placing a titanium tube into a rack, waiting for the day we finally come to bring it home. If you feel your eyelids growing heavy, allow the grand story of life on Earth to wrap around you gently and guide you into calm. Don't forget to subscribe to listen to more of our bedtime stories. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. Good night and sweet dreams of the red planet.